Okay, here's one more example from 4.3. This is example number 2D, asking us to find relative extrema, relative maximums and minimums using the first derivative test. So looking at this f of x, I have x to the fourth plus 1 over x squared. And now you should have a red flag, because I have a red flag. I notice that my function is a rational function. There's a numerator and a denominator. And so I know that my denominator could be 0, which is going to cause my function to be undefined. And so I know that there's vertical asymptote at x equals 0 on this graph. So I need to be careful with that as we go through this problem, remembering that there is no value at x equals 0 because there's a vertical asymptote there. All right, let's follow the process of finding our relative extrema with our first derivative test. Let's find the derivative. And so what derivative rule would you have to use in order to find the derivative of this f of x? Yeah, this is a quotient rule, right? It's been a while, but remember quotient rule is bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Pause your video, practice that, and see if you got the same thing I did. All right, so that's what I got for my derivative. I'm going to go ahead and distribute and combine like terms. And it looks like my derivative simplified would be 2x to the fifth minus 2x all over x to the fourth. I hope you got the same thing I did. Now that we have the derivative, we can figure out what our critical numbers are. Remember, that's when our derivative equals 0. That's the top equal to 0. And where the derivative doesn't exist. That's where the bottom equals 0. So I'm going to set up two different equations, where the top equals 0 and where the bottom equals 0, so I can find my critical numbers, where my derivative equals 0 or doesn't exist. I'm going to solve each of these equations. I'm going to set each piece equal to 0, and I'm going to get critical numbers at 0, critical numbers at plus or minus 1, and then critical numbers at 0. So I have three critical numbers, -1, 0, and 1. I'm going to go ahead and put those on my sign chart. I'm going to plug numbers in each interval, so it looks like I have to use 1, 2, 3, 4 different numbers, plugging those numbers into my derivative, so I can figure out if my derivative is positive or negative. Remember, if my derivative is positive, my function is increasing. If my derivative is negative, my function is decreasing. If my derivative changes from positive to negative, I've just found a relative maximum. If my derivative changes from negative to positive, I've just found a relative minimum. So I need you to pause the video. I need you to take a few minutes, plug in 4 different numbers in each of these intervals into your derivative so we can see if our derivative is positive or negative. Remember, we're plugging them into the derivative, so if I were you, I'd probably plug it into this simplified derivative of 2x to the fifth minus 2x all over x to the fourth. Pause the video, plug in some numbers, and then come back to me and see what you get. All right, I got negative, positive, negative, positive. Now remember, it doesn't always alternate like that. It just happens to alternate like that on this problem, but just be careful with that. So it looks like here my function, because my derivative is negative, it decreases. It then increases. Remember though, what's happening at x equals 0? Remember, that was our vertical asymptote, right? So what you should probably do is put a little symbol on your sign chart to represent that that's a vertical asymptote. You wouldn't want to draw your picture where it increases and then decreases and say that this is a relative maximum, because it's not, right? There's an asymptote there. There is no value there. And so it looks like my function decreases and then increases, hits a vertical asymptote, and then it decreases and then increases again, okay? So where do I have my relative maximum? Remember, relative maximum are when my derivative changes from positive to negative. And since the only time it changes from positive to negative is at that vertical asymptote, we can't say that that's a relative maximum because there is no number there to begin with. So on this graph, there is no relative maximum. However, there are relative minimum values. Sorry, I don't know what happened there. There are relative minimum values. There's a relative minimum value at x equals -1 and x equals +1 because my derivative changes from negative to positive. Now remember, minimums and maximums are points, and so I need you to write them as points. And so if I know that x is -1, I should be able to find the y value in my original graph where that happens by plugging in that -1 to my very original f of x function. I'm going to do the same thing when x equals +1, and that's how I got my y values. So I have relative minimums at -1, 2, and also at 1, 2, because that's where my derivative changes from negative to positive. Okay, I'm going to go ahead and squeeze in our last example here, example number 3. This one's a little bit different because this one doesn't give us an equation anymore, it gives us a picture. But it doesn't give us a picture of original f, it gives us a picture of the derivative of f. So the graph that they give us on this example is the graph of the derivative. And it's going to ask us a few things. It's going to ask us when is the original f of x increasing or decreasing, and where does f of x have local extrema, relative maximums and relative minimums. But I don't have an equation to find the derivative of, find my critical numbers, and then do my testing like I did in the last few examples. They've just given me a picture of my derivative. So we've got to be able to use this picture to find all of those things. So kind of like we did before, we found our derivative, which we already have because it's given to us. And then our second step was to typically find our critical numbers. Remember, that's when our derivative equals 0 or doesn't exist. So can we use the graph of our derivative to figure out when this derivative graph equals 0? Well, if this is the graph of the derivative, and I want to know when the derivative equals 0, isn't that mean where it touches the x-axis? And so it looks like I actually have critical numbers at 1, at 5, and at 7. Would you agree? I have critical numbers because that's where my derivative equals 0 at 1, 5, and 7. It doesn't look like there's any place where my derivative doesn't exist. There's values all the way through my function. And so I just have critical numbers where the derivative equals 0. So if those are my critical numbers, then the next step would be to take my intervals and test values, right? Just like I've been doing before. So I should be able to take a number that's less than 1, plug it into my derivative and see if it's positive or negative. Take a number between 1 and 5, plug it into my derivative to see if it's positive or negative. Plug in a number between 5 and 7, and plug in a number after 7 to see if my derivative is positive or negative. The problem, though, again, is that we don't have an equation to plug into. All we have is the graph of the derivative. But we should be able to use that graph to figure out if the derivative is positive versus negative. Look at the interval before 1. If this, if this is the graph of the derivative, is the derivative values positive or negative in this interval? Well, to me, because the graph is above the x-axis, the derivative has positive values because he's above the x-axis. So my derivative, I would say, is positive in the interval from 0 to 1. When I use the graph again and look at the interval between 1 and 5, to me it looks like my derivative values are negative because the derivative graph is below the x-axis. He has negative values. What do you think it is from 5 to 7? Yeah, it looks like my derivative is positive because it's above the x-axis. And what is the derivative values from 7 to 8? To me it looks like they're negative because they're below the x-axis. So even without an equation, as long as I have the picture of the derivative, the graph of the derivative, I can figure out if the derivative is positive or negative in the intervals that I need. So now that I have that information, I should be able to answer the full question. I should be able to now figure out where my original graph, even though I don't have it, is increasing and decreasing by just looking at the value of the derivative. So I know that my original graph f is increasing when my derivative is positive. That means my original graph f is increasing from 0 to 1, and again from 5 to 7, because the derivative is positive. I know that my original graph is decreasing from 1 to 5, and then again from 7 to 8, because that's when the derivative is negative. I should be able to tell all of that by just looking at the graph of the derivative. I can also then use my first derivative test to figure out where I have relative maximums and minimums. So I know in this graph, my function is increasing, decreasing, increasing, and decreasing again. So to me, it looks like it's increasing then decreasing. My derivative goes from positive to negative. So I have a relative maximum at x equals 1. It looks like it also increases and decreases again. My derivative goes from positive to negative at x equals 7. So it looks like I have relative maximums at x equals 1 and 7. And on this question, it didn't ask me for a point, it just asked me for the specific x values. So I can just say x equals 1 and x equals 7. I know that there are relative maximums there because the derivative changes from positive to negative. Where do I have relative minimums then? Well, it looks like I have relative minimums when my derivative changes from negative to positive, and to me that happens right here at x equals 5. When the derivative changes from negative to positive, I know that I have a relative minimum. So we should be able to find increasing, decreasing, and relative extrema all by just using my first derivative, whether that's taking an equation and finding the derivative or using the graph of the derivative to answer the questions. All right, that's the first huge chunk of 4.3. We'll do another couple of pieces in the next few videos and talk a little bit more about shapes of graphs. Let me know if you need anything.